Right now, in a small patch of the southern sky, the temperature of the universe is 70 millionths of a degree colder than it should be, and we do not yet know why. The patch sits in the constellation Eridanus. It spans approximately 5 degrees across, that is roughly 10 times the angular size of the full moon. The temperature measured in microkelvins is consistently low across the patch. The depression is unusual. The depression has been the subject of 2 decades of careful analysis. The depression has not, in any decisive way, been explained. The data that records the depression comes from satellite observations of the cosmic microwave background. The cosmic microwave background, which I will refer to as the CMB from this point onward, is the leftover radiation from the early universe. It was emitted when the universe was approximately 380,000 years old. The radiation, redshifted by the subsequent expansion of space, now reaches us at microwave wavelengths, with a temperature of just under 3 kelvins. The CMB is extraordinarily uniform. The variations from place to place in the sky are tiny, only 1 part in 100,000. But within those tiny variations, the small patches and features can be measured with great precision. The cold spot in Eridanus is one such feature. It is consistently colder than the surrounding CMB by approximately 70 microkelvins. The depression is, by current best estimates, statistically significant at the 3 to 4 sigma level. That is, the probability that such a feature occurs by chance in the standard cosmological model is approximately 1 to 5%. Small, unusual, not impossible. Tonight we are going to walk through what this might mean. You do not need to hold every number. Some you will. That is enough. The cold spot is, by current understanding, one of several anomalies in the CMB. Each anomaly is, individually, modest in significance. Together they hint at something the standard model may not fully account for, or they hint at nothing at all. The anomalies may simply be the rare statistical fluctuations that any sufficiently detailed measurement will produce. We have a couple of hours. If you have come here to rest, let this carry you. The cold spot in the cosmic microwave background is not threatening. It is, in some sense, a small anomaly in a vast measurement, waiting for its explanation. Now, let us pull back. Let us look at what the cosmic microwave background is and how the cold spot came to be noticed within it. The CMB was predicted, in essence, in the late 1940s by Ralph Alpha and Robert Herman, working from the early Big Bang theory of George Gamow. Their prediction was specific. If the universe began in a hot, dense state and expanded, there should be a leftover radiation, redshifted to long wavelengths, filling all of space. The temperature of this radiation, given the expansion factor since the early universe, would be approximately 5 Kelvin. The prediction was, at the time, not taken particularly seriously. The Big Bang theory was contested. The prediction sat in the literature for nearly 2 decades without follow-up. Then, in 1964, 2 Bell Labs engineers in Holmdel, New Jersey, named Arno Penzias and Robert Wilson, were working with a horn antenna designed for satellite communications. The antenna picked up a persistent low-level noise that they could not eliminate. They cleaned the antenna. They removed the pigeons that had nested in it. They double-checked their equipment. The noise persisted. The noise was, they eventually realized, the leftover radiation from the early universe. The temperature, as measured by the antenna, was approximately 3 kelvins, close to the original prediction. The CMB had been discovered. Penzias and Wilson received the Nobel Prize in Physics in 1978 for the discovery. The CMB became one of the central observational pillars of modern cosmology. Its existence confirmed the Big Bang theory. Its detailed properties have been measured ever more precisely over the subsequent decades. The CMB has, by current measurements, a temperature of 2.725 kelvins. The temperature varies from place to place in the sky by tiny amounts, only 1 part in 100,000. The pattern of these variations encodes information about the early universe. Different satellites have measured the variations. The COBE satellite, launched in 1989, provided the first systematic map. The WMAP satellite, launched in 2001, provided much higher resolution. The Planck satellite, launched in 2009, provided the highest resolution measurements to date. Each successive generation of measurements revealed more detail. The pattern of variations became increasingly clear. The standard cosmological model, with its specific predictions for the CMB pattern, was tested against the data and broadly confirmed. But within the broad confirmation, there were some anomalies, features that did not quite fit the standard model, features that, while individually modest, suggested that the picture might not be complete. The cold spot in Eridanus is one of those features. Let me hold the COBE observations for a moment, because the discovery of the CMB anisotropies was, in some sense, one of the great triumphs of modern observational cosmology. The COBE satellite was launched in 1989. It carried two main instruments. The first, the far-infrared absolute spectrophotometer, measured the spectrum of the CMB with extreme precision. The result, published in 1990, showed that the CMB has the spectrum of a perfect blackbody at 2.725 kelvins. The agreement was, by the standards of physics, extraordinary. The CMB is the most perfect blackbody spectrum ever measured in nature. The second instrument, the differential microwave radiometer, measured small variations in the CMB temperature across the sky. After 2 years of accumulating data, the team announced, in 1992, the first detection of CMB anisotropies. The variations were tiny, only 1 part in 100,000, but they were real. The CMB was not perfectly uniform. It contained, embedded in its background of nearly uniform temperature, the seeds of all subsequent cosmic structure. The discovery was, in the language of cosmology, transformative. The standard cosmological model predicts that the universe began nearly uniform, with small primordial fluctuations. The fluctuations grew under gravity to produce eventually the galaxies and clusters and large-scale structures we see today. The CMB anisotropies are the snapshot of the fluctuations at the moment of recombination, before they grew into the structures we now observe. The COBE results confirmed the basic picture. The CMB had the predicted blackbody spectrum. The anisotropies had the predicted statistical properties. The standard cosmological model was, in broad outline, supported. The COBE results were, in retrospect, the first taste of the kind of detailed information about the early universe that the CMB contains. Subsequent satellites have refined the picture. The WMAP satellite, launched in 2001, mapped the CMB at 30 times the resolution of COBE. The Planck satellite, launched in 2009, mapped it at 3 times the resolution of WMAP. Each successive generation of measurements has revealed more detail. The standard model has, broadly, continued to be supported, but the details have, in various places, posed puzzles. The cold spot is one such puzzle. The cold spot was first noticed in 2004. A team of Spanish researchers, led by Patricio Vielva, was analysing the WMAP first-year data using a technique called spherical wavelet analysis. The technique decomposes the CMB pattern into features of various spatial scales. By examining the distribution of features at each scale, the team could test whether the data match the predictions of standard cosmology. The standard prediction is that the CMB fluctuations are Gaussian. That is, the distribution of intensities at each point in the sky follows a normal probability distribution. The Gaussian distribution has well-known statistical properties. Any deviations from Gaussianity would be a hint of non-standard physics. Vielva and colleagues found that, at a particular scale, the southern sky contained a feature that was statistically inconsistent with Gaussianity. Specifically, there was a region of unusually low temperature that was larger and colder than the Gaussian distribution would predict. The feature, when localized, was a roughly circular region in the constellation Eridanus, with a diameter of approximately 5 degrees and a temperature depression of about 70 microkelvins. This was the cold spot. The paper, published in the Astrophysical Journal in 2004, presented the result. The statistical significance, at the time, was around the 3 sigma level. That is, the probability of such a feature occurring by chance in the standard model was estimated to be a few tenths of a percent. Subsequent work refined the significance. The cold spot was confirmed in WMAP 3-year data, then in WMAP 7-year data, then in Planck data. Each successive analysis gave broadly similar results. The cold spot was real. The statistical significance, depending on the exact method of analysis, was in the range of 3 to 4 sigma. This is the situation. We have a feature in the CMB. The feature is unusual. The feature is, by current best estimates, statistically significant at a level that demands explanation. The feature has been confirmed by multiple independent analyses of multiple independent datasets. What it is, we do not know. Stay with me here. Let me also walk through the statistical context of CMB analysis, because the question of significance is one of the central issues. The CMB pattern in the standard cosmological model is predicted to have specific statistical properties. The temperature fluctuations are predicted to be Gaussian. Their power spectrum, the distribution of variations at different angular scales, is predicted by the model. The predictions are quantitative. When we measure the CMB, we obtain a particular realization of the predicted statistical distribution. The realization is, in some sense, one sample from the distribution. Different realizations would, by chance, look slightly different from each other, but all would be consistent with the predicted distribution. To test whether a feature in the CMB is consistent with the model, we ask how often such a feature would occur, by chance, in random realizations of the predicted distribution. If the feature occurs commonly, it is consistent with the model. If it occurs rarely, it is, in some sense, in tension with the model. For the cold spot, the question is how often a feature of its size, shape, and depth would occur by chance in random realizations of the standard model's predicted CMB. Various methods have been used to estimate this probability. The estimates vary, but they generally come out in the range of 1 to 5%. A 1 to 5% probability is, in some sense, ambiguous. It is not so common that we should expect to see such a feature. It is not so rare that we should be confident the standard model is wrong. It sits in the middle, demanding attention but not demanding new physics. The matter is, in some sense, statistical. The cold spot exists. The question is what to make of its existence given the predicted distribution. Different cosmologists applying different methods reach somewhat different conclusions about the significance. This is one of the textures of statistical work in cosmology. Features are detected, significance is estimated. The estimates have their own uncertainties. The interpretations are debated. The cold spot is one of the more thoroughly studied features in modern CMB analysis. The studies have given us, by now, a fairly clear picture of its statistical properties. But the picture is consistent with multiple interpretations. Now let me walk through the candidate explanations. The first candidate, and the simplest, is that the cold spot is a chance fluctuation. The standard cosmological model predicts that the CMB has random Gaussian fluctuations. In any large enough sky map, occasional unusual features will occur by chance. The cold spot may be one of those. The probability that a feature of this size and depth occurs by chance is, by current calculations, in the range of 1 to 5%. That is small but not zero. With one CMB sky to look at, an unusual feature with a 1% probability is not, in itself, decisive evidence against the standard model. It is the kind of thing we might expect to occur in any sufficiently detailed sky map. By this candidate, the cold spot is, in some sense, expected. Rare features happen. We happen to have one. The standard model is not contradicted. This is perhaps the safest interpretation. It assumes the simplest possible explanation. It does not invoke any new physics. It does not require any modifications to the standard model. Most working cosmologists, when asked their best guess about the cold spot, give some version of this answer. The feature is real. The feature is statistically unusual, but the unusualness is not extreme enough to require new physics. It is more likely to be a chance fluctuation than anything else. The second candidate is more interesting. It involves what is called the Integrated Sachs-Wolfe effect. Let me walk through this carefully because it is, in some sense, the most well-developed alternative explanation. The Integrated Sachs-Wolfe effect, often abbreviated ISW, describes how CMB photons can lose or gain energy as they travel through evolving large-scale structures in the universe. Specifically, if a photon enters a region of higher density, it gains energy. If it then exits that region, it loses energy. In a static universe, the energy gain and loss would exactly cancel. In an expanding universe, particularly one with dark energy causing acceleration, the cancellation is imperfect. Photons traversing dense regions may gain a small net amount of energy. Photons traversing underdense regions may lose a small net amount. The CMB photons travelling toward us have, over the past 13 billion years, traversed many such structures. The total ISW effect summed over the entire path, contributes to the temperature variations we observe in the CMB for a photon that traverses a particularly large, underdense region, a supervoid. The ISW effect can produce a small but measurable cooling. The photon enters the supervoid, climbs out of the gravitational potential well of the surrounding higher density structures, and emerges with slightly less energy than it would have had without the supervoid. The cooling, integrated over a supervoid the size of 1 billion light-years or more, can produce a temperature depression of perhaps tens of microkelvins. The depression appears in the CMB as a cool spot in the direction of the supervoid. So, by this candidate, the cold spot is the imprint of a supervoid between us and the surface of last scattering. The supervoid is at some intermediate distance. Photons traversing it lose energy. The cool spot in the CMB is the consequence. This is, in some sense, an elegant explanation. It uses well-understood physics. It does not require any new beyond the standard model. It only requires that a sufficiently large supervoid exists in the right direction. The question is whether such a supervoid actually exists. In 2007, Lawrence Rudnick and colleagues claimed to detect such a supervoid using radio surveys. The result was provocative. It suggested that the cold spot's explanation was the ISW effect from a large underdense region. In 2015, István Szapudi and colleagues using infrared survey data published a more direct claim. They identified a supervoid at approximately 1.8 gigaparsecs, or roughly 6 billion light-years, in the direction of the cold spot. The supervoid spanned roughly 1 billion light-years across. The density depression was significant. If this supervoid is real, the ISW effect from it could, in principle, explain the cold spot. However, in 2017, Ruari Mackenzie and colleagues challenged the claim. Their analysis of independent data suggested that the proposed supervoid does not exist with the strength claimed. They argued that the ISW effect from any actually existing supervoid in that direction is too small to explain the full cold spot. The matter is, at present, contested. Some analyses support the supervoid explanation, others reject it. The data is not definitive. Stay with me here. The third candidate is more speculative. It involves what is sometimes called the bubble collision hypothesis. Let me walk through this carefully, because it is the candidate that most directly relates to the title of this video. In standard cosmology, the universe is described by the inflationary Big Bang model. Inflation is a period of extremely rapid expansion that is hypothesized to have occurred in the very early universe before the regular Big Bang expansion. Inflation explains several features of the universe that the standard Big Bang model alone could not, including the flatness of space, the homogeneity of the cosmic microwave background, and the spectrum of primordial fluctuations. In standard inflation, the inflation eventually ends, and the universe transitions to the regular expansion phase. The end of inflation is, in this picture, a single event that produces our observable universe. But there are variants of the inflationary picture that are more elaborate. In eternal inflation, for instance, the inflation never globally ends. Different regions of the inflationary phase end at different times, producing different bubble universes. Our observable universe is, in this picture, one such bubble. There may be many other bubbles, in different parts of the inflationary metaverse, each containing its own observable universe. This is, in some sense, a multiverse picture. The eternal inflation produces an infinite number of bubble universes. Each bubble, once inflation ends within it, expands and contains its own physics, possibly with different physical constants and laws. In some versions of eternal inflation, the bubbles can collide with each other. If two bubbles form near each other in the inflationary metaverse, they can grow large enough to overlap. The overlap produces a boundary region where the bubbles meet. For an observer inside one bubble, a collision with another bubble would, in principle, produce observational consequences. The collision could disturb the boundary of our bubble. The disturbance would, over the subsequent cosmic evolution, leave imprints on observable features. One of the most accessible imprints in this picture would be on the cosmic microwave background. A bubble collision would, in principle, produce a circular cold or hot region in the CMB with specific properties. So the bubble collision hypothesis suggests that the cold spot might be the imprint of a collision between our bubble universe and another bubble universe. This is the hypothesis. It is speculative. It rests on specific assumptions about cosmology that go beyond the standard model. It rests on specific assumptions about eternal inflation that are themselves contested. But it is, in some sense, a coherent picture. If eternal inflation is correct, and if bubble collisions can occur, and if the cold spot is the imprint of one such collision, then we have, in some sense, indirect evidence for the existence of another universe. Let me hold the conceptual development of the bubble collision picture a bit longer because it has been the subject of detailed theoretical work. In 2011, a paper by Stephen Feeney and colleagues published the first systematic search for bubble collision imprints in CMB data. They developed specific templates for what such imprints would look like, including their angular size distribution, their amplitude distribution, and their polarization signatures. They then searched the WMAP data for features matching these templates. The result was, at the time, ambiguous. They found a few candidate imprints, but none was decisively distinguishable from chance fluctuations or other features. Subsequent searches with Planck data have refined the analysis. Some of the candidate imprints have been reanalyzed. None has been confirmed at a level that would constitute discovery. The bubble collision hypothesis in this work has been treated as a serious scientific hypothesis. It has been compared quantitatively to the data. The comparison has not, at present, supported the hypothesis, but the hypothesis has been investigated with the appropriate rigor. This is, in some sense, what science can do with a speculative hypothesis. Develop specific predictions. Compare them to data. Constrain the parameter space. Even if the hypothesis is not confirmed, the work narrows the possibilities and improves the overall picture. The bubble collision hypothesis has been narrowed in this way. We now know that, if bubble collisions exist, they must be rare enough that we have not yet seen multiple, clear examples. We know they must have specific properties to match any observed candidates. We know they cannot, by current data, be the explanation for most of the anomalous features in the CMB. This is progress. The hypothesis is more constrained than it was. The investigation continues. The claim is that another universe collided with ours in the early phase of inflation. The collision left a circular imprint on the CMB. The imprint is the cold spot we observe today. This is a strong claim. It cannot be verified by current data. It cannot be ruled out by current data. The bubble collision hypothesis is, at present, one of the candidate explanations for the cold spot, but it is far from the favoured explanation. Most cosmologists, including those who take eternal inflation seriously, do not consider the cold spot to be confirmed evidence for a bubble collision. The other explanations, particularly chance fluctuation and possibly ISW from a supervoid, are considered more likely. Let me hold for a moment what the field's view of the bubble collision hypothesis is. The hypothesis has been taken seriously enough to merit substantial theoretical and observational work. Papers have been written, predictions have been made, searches have been conducted, but the hypothesis has not, in any meaningful sense, been preferred. It sits in the literature as one of the candidate explanations, with most weight on the simpler alternatives. This is in some sense the appropriate scientific attitude. We do not dismiss speculative hypotheses out of hand. We investigate them with appropriate rigor. We compare them to the data. We constrain the parameter space. We let the evidence speak. For the bubble collision hypothesis, the evidence currently does not strongly support it. The hypothesis remains a possibility, but not a leading candidate. The field's consensus is that other explanations are more likely. This consensus, however, could change. New data could shift the balance. Future polarization measurements, in particular, could be decisive. If the polarization signature is found to match a bubble collision prediction, the hypothesis would gain significant support. If it matches a chance fluctuation prediction, the hypothesis would be disfavored. We will, in time, have the data. But the bubble collision hypothesis is, in some sense, alive in the literature. It has been studied. It has been compared to the observational features of the cold spot. The features are, broadly, consistent with what a bubble collision would produce, but they are also consistent with other explanations. Stay with me here. Now let me walk through the specific signatures that a bubble collision would produce, because the discussion has been quite detailed. A bubble collision in eternal inflation cosmology would produce a circular imprint on the CMB. The imprint would have a particular angular size, set by the geometry of the collision and the subsequent cosmic expansion. The imprint would have a particular temperature profile, with a sharp boundary and a relatively uniform interior. The cold spot has these features broadly. It is approximately circular. it has a relatively sharp boundary. The interior is, by visual inspection, relatively uniform. The size, at 5 degrees, is consistent with a range of bubble collision geometries. However, the cold spot also has features that are not specifically predicted by bubble collision models. For instance, the cold spot has a particular temperature profile that, while broadly consistent with a bubble collision, is not uniquely identifying. Other explanations also produce circular cool features with relatively sharp boundaries. Specifically, the supervoid explanation, if a supervoid of the right size and depth existed, would produce a similar circular cool feature. The chance fluctuation explanation can also produce roughly circular features by random selection. So the cold spot's properties, while consistent with a bubble collision, do not uniquely identify it. The properties are also consistent with other explanations. What would uniquely identify a bubble collision is, in principle, the polarization signature. A bubble collision would produce a particular pattern of polarization in the CMB at the location of the collision imprint. The polarization pattern would be different from what other explanations would produce. Polarization measurements of the cold spot have been made, but the precision is not yet sufficient to discriminate between explanations. Future CMB experiments, including the Lightbird satellite planned for the late 2020s, will provide much better polarization data. The cold spot may, with better data, be more decisively classified. For now, the matter remains open. Let me also hold what the polarization tells us. The CMB polarization, in general, is divided into two patterns: E-mode polarization, which has a particular curl-free pattern, and B-mode polarization, which has a divergence-free pattern. Different mechanisms produce different combinations of E-modes and B-modes. For the cold spot, the polarization pattern is part of the diagnostic. Different candidate explanations predict different patterns. Current measurements are not precise enough to definitively distinguish them, but future measurements will be. The polarization of the CMB at the surface of last scattering, before any propagation effects, is set by the conditions at recombination. The conditions, including any imprints from earlier events like bubble collisions, are encoded in the polarization pattern. If a bubble collision occurred, its imprint on the recombination conditions would be reflected in the polarization at the cold spot location. The specific pattern would be distinctive. Similarly, a supervoid would affect the polarization differently from a bubble collision. A chance fluctuation would produce yet a different pattern. The future polarization measurements, when they reach sufficient precision, should be able to discriminate among these. The discrimination will be the key to resolving the cold spot's nature. We continue to await the better data. Stay with me here. Now let me hold what would have to be true for the bubble collision hypothesis to be correct. The first thing is that eternal inflation must be the correct cosmological model. Standard inflation, without the eternal extension, does not produce multiple bubbles, so the picture requires that we accept eternal inflation as the correct cosmology. Eternal inflation is, by some analyses, a natural consequence of certain inflationary models. By other analyses, it is a problematic feature that may not be physically realized. The matter is contested. The second thing is that bubble collisions must actually occur. In some versions of eternal inflation, collisions are common. In other versions, they are rare or absent. The rate of collisions depends on details of the inflationary model that we do not, at present, have direct observational access to. The third thing is that the collision must produce a detectable imprint. Some calculations suggest that bubble collisions would produce subtle features that we could detect. Other calculations suggest that the features would be wiped out by subsequent cosmic processes. The fourth thing is that our particular cold spot must be the result of such a collision, rather than the result of one of the other candidate explanations. When all four conditions are required, the bubble collision hypothesis is, in some sense, demanding. It requires that several specific things all be true. The probability that all four conditions hold is, by various estimates, not high. But the conditions are also not individually refuted. We do not have evidence against eternal inflation. We do not have evidence against bubble collisions. We do not have evidence against a collision producing detectable imprints. We just do not have positive evidence for any of them. So the hypothesis sits in the literature as a possibility. It cannot be ruled out. It also cannot be definitively confirmed. Let me hold this for a moment. The picture, when we sit with it, is that the cold spot is one of the loose threads of modern cosmology. It is a feature in our best data that does not have a definitively settled explanation. Multiple candidate explanations exist. Each is consistent with the data. Each makes some predictions that could, with future data, distinguish them. The most exotic candidate, the bubble collision, would, if correct, suggest that another universe touched ours in the deep past, and that we now see the imprint of that touch in our cosmic microwave background data. This is, in some sense, the strangest implication that the cold spot might have. It is also, by current best estimates, far from the most likely explanation. But it is, in some sense, one of the possibilities that the data admits. Now let me bring this closer. I want to walk through what the cold spot would imply if the bubble collision hypothesis were correct. The first implication is that the multiverse exists. Our universe would, in this picture, be one of many. Other universes in other bubbles would also exist. Some of them might have different physical laws. Some of them might be similar to ours. The multiverse picture is, in some sense, a profound revision of our cosmological self-understanding. It moves us from being the only universe to being one universe among many. The implications for our self-understanding, our sense of cosmic position, our cultural narratives, would be substantial. The second implication is that our universe has, at some point in its history, interacted with another universe. The interaction was not gentle. It produced a measurable effect on our cosmic microwave background. The other universe, while not present in any current observable sense, has left its mark. This is, in some sense, evidence of cosmic interaction at a level beyond our normal experience. Our universe is not isolated, it has neighbours. The neighbours are, in some sense, real. The third implication is that we have, by careful observation, detected indirect evidence of the multiverse. The cold spot is the signature. It is the trace left by the collision. By measuring the trace, we have, in some sense, detected the existence of another universe. This would be one of the most important discoveries in the history of physics. It would change our cosmological understanding in profound ways. But, again, this is contingent on the bubble collision hypothesis being correct. We do not know if it is. The hypothesis is one candidate among several. The other candidates are considered, by most working cosmologists, more likely. Stay with me here. Let me walk through what we know about eternal inflation in more detail, because the bubble collision hypothesis hinges on it. Eternal inflation, as a cosmological framework, was developed in the early 1980s by Alan Guth, Andrei Linde, Alex Vilenkin, and others. The basic idea is that in the inflationary epoch, the inflation does not end uniformly. Different regions of the inflating space transition out of inflation at different times. The transitions produce bubble universes, each of which contains a region of post-inflation space. The inflation, in some regions, continues forever. In other regions, it ends. The ending regions become the bubbles. The continuing regions provide the medium in which more bubbles can form. If we are in one such bubble, then we have a particular region of post-inflation space, surrounded by presumably a still inflating exterior. The exterior is, in some sense, the metaverse. The metaverse contains many only bubbles, possibly an infinite number. This is the picture. It is, by the lights of inflationary cosmology, a natural extension of the standard inflation model. It is not, in this view, an exotic addition. It is what inflation naturally produces if certain conditions hold. Whether the conditions hold is, of course, a deep question. Different inflationary models give different answers. Some models predict eternal inflation as a generic outcome. Others do not. The current consensus in cosmology is that eternal inflation is, in some sense, a plausible possibility but not an established fact. The matter is one of theoretical investigation. The matter is not directly testable in any obvious way. Bubble collisions in this framework would occur if two bubbles formed near each other in the metaverse and grew large enough to overlap. The probability of such collisions depends on details of the inflationary dynamics that are not well constrained. Some calculations suggest that bubble collisions should be common, in the sense that any given bubble would have multiple collisions over its history. Other calculations suggest that collisions would be rare. The matter depends on the specifics of the inflationary model. If our bubble has had collisions, the imprints might be detectable in the CMB. The cold spot is, in this picture, one candidate for such an imprint. But there is no positive evidence that it is, in fact, a collision imprint, rather than some other kind of feature. This is the situation. The bubble collision hypothesis is, in some sense, a possible interpretation of the cold spot. The hypothesis rests on speculative, cosmological frameworks. The data does not at present decisively support or refute the hypothesis. Let me also walk through what other multiverse pictures exist beyond the eternal inflation one. The notion that our universe is one of many has been proposed in several different theoretical frameworks. The eternal inflation multiverse is the picture I have been discussing. It says that inflation never globally ends, with different regions transitioning out at different times to produce bubble universes. Another multiverse picture comes from string theory. The string theory landscape contains many possible vacuum states, each corresponding to different effective physical laws. If different regions of the universe sit in different vacuum states, they would effectively be different universes with different physics. Another picture comes from the many worlds interpretation of quantum mechanics, which I discussed in another video. In that picture, the universal wave function has many branches, each containing a version of the universe. Another picture comes from level 3 or modal multiverses, in which our universe is just one of many mathematically possible universes, each of which is, in some sense, real. These different multiverse pictures are conceptually distinct. They arise from different theoretical considerations. They have different structures and different implications. The bubble collision hypothesis is specifically about the eternal inflation multiverse. A bubble collision is a phenomenon predicted by eternal inflation. The other multiverse pictures do not generally predict bubble collisions in the same way. So when we ask whether the cold spot might be evidence for the multiverse, we are asking specifically about the eternal inflation version. The other multiverse pictures, even if correct, would not, by themselves, predict the cold spot. This is a useful distinction. The cold spot, if it is exotic evidence at all, is evidence for one specific multiverse picture, not for any general notion of multiple universes. Let me also walk through what the cold spot's existence depends on. The cold spot is a feature in our CMB data. The data depends on the satellites that collected it, the analysis methods that processed it, and the statistical frameworks that interpreted it. The cold spot has been detected in multiple independent datasets. The WMAP data showed it. The Planck data confirmed it. Various ground-based experiments have also seen it. The detection is, in this sense, robust across instruments. The cold spot has been analysed by multiple independent methods: wavelet decomposition, real space variance, harmonic analysis, comparison with simulations. The results are broadly consistent across methods. The feature is, in this sense, robust across analysis techniques. The cold spot has been interpreted by multiple independent researchers. Different research groups have applied different theoretical frameworks. The interpretations differ in their preferred explanation, but the basic phenomenology is agreed upon. So the cold spot, as a feature, is on firm ground. It is established. The question is not whether it exists. The question is what causes it. This is the situation: a robust feature with uncertain explanation. The investigation continues. Now let me walk through the other CMB anomalies to put the cold spot in context. The cold spot is not the only anomaly that has been identified in the CMB. There are several others. Each is, individually, modest in significance. Together, they hint at something the standard model may not fully account for. One anomaly is the hemispherical asymmetry. The CMB shows slightly different statistical properties in opposite hemispheres of the sky. Specifically, the northern hemisphere has somewhat smaller temperature variations than the southern hemisphere. This asymmetry is, by current measurements, statistically significant at the level of a few sigma. Another anomaly is what is sometimes called the axis of evil. Several of the larger scale features in the CMB appear to align with each other and with the ecliptic, the plane of the solar system. The alignment is, in the standard cosmological model, unexpected. The standard model predicts that large-scale features should have random orientations. Another anomaly is the low octopole. The amplitude of the octopole component of the CMB, which describes variations on the larger scales, is somewhat smaller than expected. And there are several smaller anomalies, each individually modest but cumulatively suggestive. The cumulative significance of these anomalies taken together is harder to estimate than the significance of any individual feature. Some analyses suggest that, taken together, the anomalies are statistically significant, at a level that demands explanation. Other analyses suggest that the combination is consistent with the standard model, given that we are looking at many possible types of anomalies and any large dataset will produce some. This is, in some sense, a question of multiple comparison statistics. If we test the data for many possible types of anomalies, we are likely to find some by chance. The combination of cold spot, hemispherical asymmetry, axis of evil, and low octopole may or may not be statistically excessive, depending on how we count the trials. The matter is, again, contested. Different cosmologists reach different conclusions. Let me hold this for a moment. Let me hold the question of what we should expect from the CMB if the standard model is correct. The standard model predicts with great precision the statistical properties of the CMB. Specifically, the CMB anisotropies are predicted to be Gaussian, with a power spectrum given by the model's parameters. In any random realization of this prediction, certain features would occur. Hotspots and cold spots of various sizes and intensities. The distribution of these features in any single realization would be statistical. A single realization is, in some sense, just one sample from the predicted distribution. If we look at our CMB sky, we see one such realization. The realization, broadly, matches the predictions. But it also has by chance some features that are at the unusual end of the distribution. The cold spot is, in this analysis, at the unusual end. By some measures, it is in the top 1% of possible features. By other measures, it is in the top 5%. The exact significance depends on details of the analysis. A 1% feature is, in some sense, expected. In any sufficiently detailed dataset, features at this level of unusualness will occur. The fact that we see one such feature is not by itself evidence against the standard model. But a 1% feature is also worth noticing. It is worth investigating. It is worth asking whether there might be physical reasons for its specific properties, beyond chance. This is the dual character of the cold spot. It is expected, in the sense that the standard model allows features of this level of unusualness. It is also worth investigating, in the sense that it might have a non-chance explanation. The investigation has been productive, even if it has not produced a definitive conclusion. The picture, when we sit with all of this, is one of accumulated tensions. The standard cosmological model, while broadly successful, has small but real tensions with the data. The tensions appear in the CMB anomalies, in the Hubble tension I discussed in another video, in various other smaller discrepancies. Each tension is individually small. The cumulative effect, however, is significant. The standard model, by these accumulated tensions, may be in need of modification. What modification we do not yet know. Multiple candidates exist. Each addresses some of the tensions. None addresses all of them. The picture, in current cosmological research, is one of active investigation. The cold spot is one of the features that contributes to the picture. Its presence is established. Its explanation is open. This is, in some sense, the texture of working on the foundations of cosmology. We have a good model. The model has small tensions with the data. The tensions are subjects of investigation. The investigation is ongoing. Stay with me here. Let me also walk through the supervoid hypothesis in more detail because it has received the most observational attention. The supervoid hypothesis says that a large, underdense region between us and the surface of last scattering produces the cold spot via the integrated Sachs-Wolfe effect. For this to work, the supervoid must be large enough and deep enough to produce a temperature depression of about 70 microkelvins. Calculations suggest that a supervoid with a radius of approximately 1 billion light-years and a density depression of perhaps 30% below the cosmic mean would produce roughly the right effect. Whether such a supervoid actually exists in the direction of the cold spot is the empirical question. The original Rudnick et al. Claim in 2007 suggested that radio surveys showed a deficit of galaxies in that direction. The result was provocative but not definitive. The radio survey data has its own uncertainties, and the interpretation of any density deficit as evidence for a supervoid is sensitive to assumptions. The Szapudi et al. Claim in 2015 used infrared survey data from the WISE satellite. The team identified, in the direction of the cold spot, a region of below-average galaxy density. They estimated the size and depth of the underdensity and concluded that it could account for much, though perhaps not all, of the cold spot. The Mackenzie et al. Response in 2017 challenged the claim. Using independent data, they argued that the proposed supervoid is not, in fact, present at the required strength. They suggested that the cold spot is more likely a chance fluctuation. The debate has continued since. Various analyses have come down on different sides. The matter is not settled. What the debate illustrates is the difficulty of measuring large-scale density variations at intermediate cosmological distances. The galaxy surveys we have cover certain volumes with certain levels of precision. Larger and deeper surveys are needed to definitively map the density distribution at the relevant scales. The DESI survey, currently ongoing, and the Vera Rubin Observatory, beginning full operations in 2026, will produce better galaxy density maps. The maps should, within the next decade, settle whether the proposed supervoid in the direction of the cold spot actually exists. If the supervoid does exist, and is large enough, then the integrated Sachs-Wolfe effect from it could explain the cold spot. The bubble collision hypothesis would lose support by Occam's razor. We would not need an exotic explanation when an ordinary one suffices. Let me also walk through what we know about the early universe in more general terms to place the bubble collision hypothesis in context. The standard cosmological model has the universe beginning in a hot, dense state, undergoing inflation, transitioning to ordinary expansion, forming the cosmic microwave background at 380,000 years, forming stars and galaxies, and continuing to expand to the present. The model is consistent with a vast range of observations: the CMB pattern, the expansion rate, the abundance of light elements, the growth of structure, the accelerating expansion. All of these are accommodated within the standard framework, but the model has loose ends. We do not know what dark matter is. We do not know what dark energy is. We do not know what triggered inflation. We do not know why the inflation lasted the duration it did. We do not know what physics governed the inflationary epoch. Each of these unknowns represents an opportunity for new physics. Various proposals have been made for each. None has been definitively confirmed. The bubble collision hypothesis is, in this sense, one of many speculative ideas that touch on the unknown corners of the standard model. Eternal inflation is one possible inflationary model. Bubble collisions are one possible consequence of eternal inflation. The cold spot is one possible signature of a bubble collision. Each link in this chain is, at present, unconfirmed. The overall hypothesis is speculative, in the sense that all the links would need to be true for the conclusion to follow. But the chain is internally coherent. Each link is, individually, taken seriously by some researchers. The chain represents a possible, coherent extension of our standard cosmological picture. This is, in some sense, the status of speculative cosmology: chains of plausible but unconfirmed hypotheses. Each chain represents a possible extension of the standard model. The actual extensions, when they come, will need to be supported by direct evidence. The cold spot might, in principle, provide such direct evidence for one such chain, but it has not yet been confirmed in this role. If the supervoid does not exist, then the cold spot's explanation remains open. The chance fluctuation explanation would gain support. The bubble collision hypothesis would also remain on the table, since it does not require any particular feature in the galaxy distribution. Let me hold what the chance fluctuation explanation actually entails. The standard model predicts random Gaussian fluctuations in the CMB. In any sufficiently large patch of sky, some unusual features will occur. The cold spot in this picture is one such feature. The probability of a chance fluctuation matching the cold spot's specific properties is, as I have said, in the range of 1 to 5%. This means that, if we look at many possible random realizations of the CMB, between 1 in 20 and 1 in 100 would contain such a feature. We have one CMB sky to look at. The fact that we see such a feature is, in this picture, not particularly remarkable. It is at the unusual end of the distribution, but it is within the range of what the standard model predicts. The chance fluctuation explanation is, in some sense, the null hypothesis. It is what we would expect if no special mechanism produces the cold spot. The other candidate explanations are, in some sense, alternatives to this null. For each alternative to be preferred over the null, we need evidence that goes beyond the cold spot itself. We need either direct observation of the alternative mechanism, a confirmed supervoid, a confirmed bubble collision, or a pattern of features that the null cannot easily produce, multiple correlated anomalies that all fit a particular alternative. At present, we do not have such evidence. The null hypothesis remains a viable explanation. The alternatives remain candidates but not preferred. This is in some sense the default scientific position. Without positive evidence for an alternative, we maintain the null. The cold spot in this position is a chance fluctuation until proven otherwise. Most working cosmologists hold this position. They consider the cold spot to be probably a chance fluctuation, with the alternatives being possibilities worth investigating, but not preferred explanations. We will, in the next decade, have better data. The picture will presumably become clearer. Now, let me bring this closer to the question of what the cold spot might say about other universes. The bubble collision hypothesis is, as I have said, one of the candidate explanations for the cold spot. The hypothesis is speculative. The hypothesis cannot be tested with current data. The hypothesis sits in the literature as a possibility. If the hypothesis were correct, what would it tell us about the other universe? The first thing it would tell us is that the other universe exists. This is, in some sense, the most fundamental fact. The other universe is real. It occupies its own region of the eternally inflating metaverse. The second thing it would tell us is that the other universe has, in some sense, physics that is broadly compatible with ours. The collision produced an effect that we can interpret in terms of our physics. The other universe is not, in this picture, so radically different that interaction with it is incomprehensible. The third thing it would tell us is something about the timing of the collision. By analysing the imprint, we could, in principle, determine when the collision occurred. The timing would be early, in the inflationary phase, before our observable universe had reached its current configuration. The fourth thing it would tell us is the direction of the other universe. The cold spot is located in Eridanus. The other universe in this picture would be in that direction, beyond our cosmic horizon. This is what the hypothesis would say, if correct. But again, the hypothesis is not the favoured explanation. The cold spot is more likely, by current best estimates, to be a chance fluctuation or the imprint of a supervoid. The bubble collision hypothesis is a possibility that has not been ruled out, but it is not the leading candidate. We do not, in any decisive way, have evidence for the existence of another universe. We have, at most, a feature in our data that one speculative hypothesis would associate with such evidence. This is the honest situation. Stay with me here. Let me also hold the philosophical implications of what we have been discussing. The cold spot, if it is the imprint of another universe touching ours, would be a profound discovery. It would be the first observational evidence of cosmic structures beyond our own universe. It would suggest that the multiverse is real, not just a theoretical construct. This is, in some sense, a tantalizing prospect. The history of science has repeatedly produced discoveries that expand our cosmological imagination. The discovery of other galaxies, the discovery of cosmic expansion, the discovery of the cosmic microwave background, the discovery of dark matter and dark energy. Each was, in its time, a profound expansion of our picture of the cosmos. Detection of another universe through CMB imprints would be, perhaps, the next such expansion. We would learn that our cosmos is not alone. But, as I have emphasized, the evidence for this is currently weak. The cold spot is, by current best understanding, more likely to be a chance fluctuation or a supervoid imprint than a bubble collision signature. The exotic interpretation is not, in any decisive sense, supported by the data. What we have is the possibility. We do not have the confirmation. The possibility itself, however, has value. It expands what we consider when we think about cosmology. It enriches our hypotheses. It pushes the boundaries of what we take seriously. If the cold spot eventually turns out to be a chance fluctuation, we will have learned, in the process of investigating it, much about the standard model's statistical predictions, about the cosmic microwave background, about the structure of the cosmos. The exotic hypothesis will not have been confirmed, but the investigation will have been productive. If the cold spot turns out to be a supervoid imprint, we will have learned about the integrated Sachs-Wolfe effect and about large-scale density variations in the intermediate distance universe. The exotic hypothesis will not have been needed. If the cold spot turns out to be a bubble collision signature, we will have, in some sense, observed evidence for another universe. The implications would be profound. Let me hold the practical aspects of how researchers approach the cold spot. Different research groups have different specializations. Some focus on data analysis. They develop the statistical methods used to identify features and assess significance. Others focus on theoretical modeling. They develop the predictions for what various explanations would entail. Others focus on observational follow-up. They design and conduct experiments that can distinguish between explanations. The combined effort across many groups is what produces the cumulative picture. Each group contributes a particular piece. The pieces combine to give the field a comprehensive understanding. For the cold spot, this collective effort has produced over 2 decades a substantial body of work, hundreds of papers, many independent analyses, many proposed interpretations. The work is in some sense characteristic of how modern cosmology proceeds. What is striking, perhaps, is how a single small region of the cosmic microwave background, a region only 5 degrees across, only tens of microkelvins cooler than its surroundings, has prompted such extensive investigation. The investigation is, in some sense, proportional to the importance of the question. If the cold spot is, in fact, evidence of another universe, the implications are profound. If it is a chance fluctuation, the investigation has still produced valuable methodological work. This is the calculation that the field has, implicitly, made. The cold spot is worth investigating because the potential implications are large. Even if the most exotic interpretation is unlikely, it cannot be ruled out, and ruling it out is itself valuable. The investigation continues. Each of these outcomes is, in some sense, productive for our understanding. The cold spot is, regardless of its ultimate explanation, a feature worth studying. Now let me walk through what future data might tell us. Because the cold spot, while currently mysterious, may, with better data, become clearer. The next generation of CMB experiments will provide higher resolution polarization data. The polarization patterns can, in principle, distinguish between the different candidate explanations for the cold spot. Different explanations predict different polarization signatures. The Lightbird satellite, planned for launch in the late 2020s by the Japan Aerospace Exploration Agency, will measure CMB polarization with unprecedented precision. The Simons Observatory, currently under construction at Cerro Toco in Chile, will also contribute to the polarization measurements. The CMB S4 project, in earlier stages of planning, would provide even better precision. If the cold spot has, embedded in its polarization, a specific signature consistent with a bubble collision, then the hypothesis would gain significant support. If the polarization is consistent with the chance fluctuation explanation, the bubble collision hypothesis would lose support. If the polarization is consistent with the supervoid explanation, that hypothesis would be favored. The next decade of CMB experiments will, in principle, distinguish between these scenarios. The cold spot's nature should be clearer by the late 2030s. In the meantime, the cold spot remains one of the open puzzles of modern cosmology. Let me also walk through what other observations might help. The CMB is not our only window into the early universe. Other observations, particularly of the large-scale structure of galaxies and the early gas distributions, contribute to our cosmological picture. Let me hold one more aspect of the polarization measurements. The CMB has, in addition to its temperature variations, polarization variations. The polarization is produced by Thomson scattering of CMB photons of free electrons in the early universe. The pattern of polarization encodes additional information about the conditions of the early universe. Different mechanisms that produce CMB features have different polarization signatures. A bubble collision would produce a particular pattern of polarization at the collision location. A chance fluctuation would produce a different pattern. A supervoid imprint would produce yet a different pattern. If we can measure the polarization with sufficient precision, we can, in principle, distinguish between these mechanisms. The mechanism that produces the observed polarization pattern at the cold spot location is, by this analysis, the most likely explanation. Current polarization measurements from Planck and ground-based experiments are not yet precise enough at the relevant scales to definitively distinguish the explanations. The signals are small, the precision is limited. Future experiments, particularly Lightbird and the Simons Observatory, will improve the polarization measurement substantially. The improvements should, within the next decade, allow us to discriminate between the major candidate explanations. If the cold spot's polarization pattern when measured with sufficient precision, is consistent with a bubble collision, the hypothesis will gain significant support. If it is consistent with a chance fluctuation, the hypothesis will be disfavored. If it is consistent with a supervoid, the matter will be settled in favor of that explanation. The next decade will, in principle, give us the data we need. We will see what it tells us. Let me hold for a moment what would happen if the resolution comes in favor of the chance fluctuation explanation. Such a resolution would mean that the cold spot, despite its visual striking appearance, is not a marker of anything beyond the standard model. It is, in some sense, just the kind of feature that the standard model occasionally produces. This would be, in some ways, a deflating outcome. The exotic hypotheses would be dismissed. The standard model would be reaffirmed. The cold spot would lose its scientific significance. But the deflation would not, in itself, be a loss for science. The work done to investigate the cold spot would have been valuable methodologically. The constraints on the alternative explanations would help refine our understanding of the possible explanations for cosmological anomalies in general. And, importantly, the resolution would, in some sense, mean that the standard cosmological model is even more successful than we currently estimate. The model would have accommodated yet another seemingly anomalous feature. The model's predictive scope would be confirmed. For the field, this would be a vindication. The model works. The unusual features are expected. No new physics is needed. Different researchers, of course, would react differently. Those who were hoping for confirmation of exotic hypotheses would be disappointed. Those who were skeptical would be vindicated. The field as a whole would in some sense move on. The cold spot would, in this scenario, become a historical footnote, an interesting feature that was investigated and found to be ordinary. The investigation would be remembered as a productive exercise that, in the end, did not require new physics. If, on the other hand, the resolution comes in favour of one of the exotic explanations, the impact would be much larger. The standard model would need to be extended. New physics would have been confirmed. The cold spot would become a landmark discovery. Which way the resolution goes, we do not yet know. We continue to investigate. Let me hold one more aspect. The cold spot, even if it is ultimately just a chance fluctuation, has served as a focus for substantial work in the foundations of cosmology. The work has improved our methods, sharpened our theoretical predictions, and clarified our understanding of the standard model. This is, in some sense, what scientific puzzles do. They focus attention, they prompt analysis, they produce, even if the puzzle itself is not deeply meaningful, valuable methodological work. The cold spot has done this for us. The methods developed to study it can be applied to other features. The theoretical frameworks developed to interpret it can be applied to other hypotheses. The data analysis techniques can be applied to future experiments. So even if the cold spot turns out, in the end, to be a chance fluctuation with no special significance, the work it has prompted is itself valuable. The investigation has been, in a meaningful sense, productive. This is one of the textures of how science develops. Specific puzzles drive general advances. The cold spot is one such puzzle. If the cold spot is, in fact, the imprint of a supervoid, then the supervoid should be visible in galaxy surveys. We should see, in the direction of the cold spot, a region of below-average galaxy density. The size and depth should match the requirements for explaining the cold spot. If the supervoid is real and has the right properties, this would settle the matter in favour of the supervoid explanation. The cold spot would be a known consequence of a known structure. If, on the other hand, no such supervoid exists, then the cold spot's explanation must be sought elsewhere. The bubble collision hypothesis would, by default, remain viable. So galaxy surveys are, in some sense, one of the keys to settling the question. The DESI survey is collecting the relevant data. The Vera Rubin Observatory will add more. Within a decade, we should have a clear picture of whether the supervoid exists. Beyond galaxy surveys, we have other observations. Gravitational lensing of the CMB provides additional information about the distribution of matter between us and the surface of last scattering. The lensing patterns can constrain the density distribution along various lines of sight. If a supervoid exists in the direction of the cold spot, the gravitational lensing signature might confirm its presence. We also have observations of the kinetic Sunyaev-Zeldovich effect, which measures the bulk motion of gas in galaxy clusters via the cosmic microwave background. This effect can probe density variations on intermediate scales. It is, in principle, sensitive to the kind of large-scale structures relevant to the supervoid hypothesis. The combination of CMB measurements, galaxy surveys, and various secondary effects should, over the next decade, give us a much clearer picture of the density distribution between us and the surface of last scattering. The cold spot's explanation should, by that time, be clearer. We will, in some sense, know much more about our cosmic neighbourhood in the next decade than we know now. Let me hold one more aspect of the bubble collision hypothesis, which is what it would tell us about cosmic history. In the bubble collision picture, our universe is one of many bubbles in an eternally inflating metaverse. Each bubble has its own internal history, beginning from the moment inflation ended within it. The histories may be similar or different depending on the random outcomes of the inflationary dynamics. A bubble collision in this picture would have occurred during the inflationary phase. Specifically, the collision would have occurred while our bubble was still growing inside the eternally inflating exterior. The collision would have disturbed the boundary of our bubble. The disturbance would have propagated through the subsequent cosmic evolution. The recombination, at 380,000 years after the Big Bang, would have preserved the imprint of the disturbance. The CMB pattern, as we see it today, would carry the imprint as a circular cold or hot region. So if the cold spot is a bubble collision imprint, it dates back to events during inflation. The events were billions of years before our universe had even formed its first stars. The events occurred at energy scales far beyond anything we have ever directly observed. The imprint, in this picture, is one of the oldest features of the cosmos that we can observe. It is older than the cosmic microwave background itself, in the sense that the events that produced it preceded the emission of the CMB. This is, in some sense, what makes the hypothesis attractive, even if it is unlikely. The possibility of accessing events from inflation, the earliest cosmic epoch, through their CMB imprints is, in itself, an interesting prospect. The cold spot may or may not be such a record. The investigation continues. Now let me hold the broader picture. The CMB is, in some sense, our most direct window into the early universe. It records the state of the cosmos at 380,000 years after the Big Bang. The features encoded in the CMB are, in some sense, the seeds of all subsequent structure. The patterns we measure today reflect the conditions of the early universe. The patterns are, broadly, consistent with the standard cosmological model. But there are small features that may, in some sense, encode information about events even earlier than the recombination, possibly events from the inflationary phase, or before. If the cold spot is, in fact, the imprint of a bubble collision, it would be one such pre-recombination feature. The collision would have occurred during inflation. Its imprint would have been propagated through the subsequent cosmic evolution to the recombination surface, where it became part of the CMB pattern. So the cold spot, if correctly interpreted in this way, would be our oldest direct evidence of cosmic events. It would predate by a significant margin the events we normally have observational access to. This is, in some sense, what makes the bubble collision hypothesis intellectually attractive, even if it is not the most likely explanation. The possibility of accessing pre-recombination events through their CMB imprints is in itself an interesting prospect. Whether the cold spot is, in fact, such an imprint, we do not yet know. Stay with me here. Now let me walk through what we have learned from the cold spot story so far, regardless of its ultimate explanation. The cold spot has, over the past 2 decades, been the subject of intense scrutiny. Multiple methods of analysis have been applied to it. Multiple candidate explanations have been developed. Multiple datasets have been used to test the explanations. The cumulative effect is, in some sense, an improvement in our understanding of the CMB. We now have much better statistical tools for analysing CMB data. We understand the integrated Sachs-Wolfe effect in more detail. We have better models of how various features could appear in the data. We have better intuition about what is and is not consistent with the standard cosmological model. Even if the cold spot turns out to be a chance fluctuation, the work on it has been productive. The work has, in some sense, refined our understanding of the CMB and our methods of analysis. This is one of the textures of cosmological research. Unusual features, when noticed, become subjects of careful study. The study, even if it does not produce definitive answers, deepens the understanding of the field. The cold spot has been one such feature. The study has been ongoing. The deepening of understanding has been substantial. The explanation remains for now open. Let me hold this. The picture, when we sit with all of this, is one of cosmology in active development. The cosmic microwave background is, in some sense, fully mapped at current resolutions. The mapping shows broadly what the standard model predicts. But it also shows small features that may or may not be inconsistent with the model. The cold spot is one of those small features. Its significance is uncertain. Its explanation is open. Its implications, if it turns out to be more than a chance fluctuation, could be profound. We continue to study it. The future data will presumably tell us more. Stay with me here. Let me also walk through what the cold spot looks like in actual CMB sky maps. Because the visual appearance, while not directly addressing the physics, gives a sense of what we are talking about. The Planck satellite produced in 2013 a high-resolution map of the CMB temperature variations. The map shows the entire celestial sphere, with each pixel coloured according to the local CMB temperature. The variations are small, only one part in 100,000, but they are visible in the colour-coded map. Most of the map looks like a noise pattern, random hot and cold spots scattered across the sky. The pattern is, statistically, what the standard cosmological model predicts. Small features, random orientations, no obvious large-scale anomalies. But in the southern hemisphere, in the constellation Eridanus, there is a distinctive feature, a region of unusually low temperature, roughly circular, about 5 degrees across. The region is visible in the map as a noticeable blue patch against the surrounding mottled background. This is the cold spot. The patch is, to the eye, anomalous. It does not look like the random pattern that surrounds it. It looks, in some sense, like a real feature. But the eye is, in this case, not the most reliable judge. The eye is prone to pattern recognition that goes beyond what the data justifies. A more careful statistical analysis is needed to determine whether the feature is, in fact, anomalous. The careful analyses, as I have walked through, have produced a significance estimate of 3 to 4 sigma. The feature is real, in the sense that it appears in multiple independent analyses. The feature is, statistically, unusual, in that it would occur with probability of only 1 to 5% in random realizations of the standard model. These are, in some sense, two ways of describing the same thing. The feature is anomalous to the eye. The feature is anomalous to careful statistical analysis. The feature is, by these measures, real and unusual. What it is, beyond being real and unusual, we do not know. Let me also walk through what we have learned about cosmic anomalies more generally. Over the past few decades, several anomalies have been identified in cosmological data. Some have been resolved. Others remain open. The earliest cosmological anomaly to gain widespread attention was the so-called Hubble tension, which I have discussed elsewhere. The tension between local and CMB-derived measurements of the Hubble constant has grown more significant over time. The resolution remains open. Other anomalies include the muon anomalous magnetic moment, the cosmological constant problem, the matter-antimatter asymmetry, and several smaller features in specific datasets. Each of these anomalies represents a small discrepancy between our best theoretical predictions and our observations. Each could in principle be a marker of new physics, or each could be a statistical fluctuation, or a systematic error in measurement, or a feature of our theoretical models that we have not yet correctly understood. The cold spot fits into this broader pattern of cosmological anomalies. It is one of several features that the standard model does not fully predict. The cumulative effect of these anomalies is, in some sense, suggestive of room for refinement in our cosmological understanding. Whether any of the anomalies will, individually, lead to definitive new physics, we do not yet know. Each is being investigated. Each is the subject of ongoing work. The cold spot is one of the more directly interpretable of these anomalies. It is, in some sense, well defined, a specific feature in a specific region of the CMB with specific properties. We can study it precisely. We can compare it to specific predictions. This is, perhaps, why the cold spot has attracted as much attention as it has. It is concrete. It is studiable. It is, in some sense, an attractive scientific target. Now let me come, slowly, to a quiet close for tonight. We have walked through the cold spot. We have walked through its discovery in the early WMAP data. We have walked through the candidate explanations. chance fluctuation, integrated Sachs-Wolfe effect from a supervoid, primordial fluctuation, bubble collision, and exotic objects. We have walked through what each explanation would entail. We have walked through the current status of the debate. The current status is that the cold spot is real. It is statistically unusual. It has not been definitively explained. Multiple candidate explanations remain in the literature. The most exotic candidate, the bubble collision hypothesis, suggests that another universe touched ours in the deep past and left an imprint we can now see. Let me hold this for one more moment. The picture, even as a possibility, has a particular quality. We sit in our small slice of the universe and consider the possibility that another universe touched ours billions of years ago, and that the touch left a mark that we can now see. The picture, even unconfirmed, is one of cosmic interconnection across what would otherwise be insurmountable distances. This is, in some sense, what makes the picture intellectually attractive. It connects us, hypothetically, to phenomena outside our universe. It suggests that the cosmos may be richer than our standard models indicate. It suggests that we may, through careful observation, be able to detect indirect evidence of other cosmic structures. Whether this is correct, we do not know. We continue to investigate. The hypothesis is, I want to emphasize, speculative. It is not the favored explanation. Most cosmologists consider chance fluctuation or supervoid imprint to be more likely. But the hypothesis sits in the literature as one of the possibilities. It cannot be ruled out by current data. Future CMB experiments, particularly those with better polarization sensitivity, may be able to distinguish between the candidate explanations. We may, within the next decade or two, have a clearer picture of what the cold spot is. In the meantime, we have the cold spot. We have its mystery. We have its candidate explanations. We continue to study it. This is where we are. Let me hold one more thought. The cold spot, in its physical reality, is a region of the cosmic microwave background. The region is small relative to the whole sky. It is, in some sense, easy to overlook, but the cold spot has, over 2 decades, accumulated significance. It has been studied, debated, and contextualized. It has become one of the well-known features of modern cosmology, despite being only a small region in the southern sky. This accumulation of significance is, in some sense, characteristic of how scientific puzzles grow. A single observation triggers attention. The attention leads to more observation. The observation leads to theoretical work. The theoretical work suggests further observations. The cycle continues. The cold spot has gone through this cycle for 2 decades now. The cycle continues. The investigation is, in some sense, a self-sustaining process. As long as the explanation remains open, the work continues. This is not, in itself, a problem. It is the natural rhythm of how deep questions are addressed in physics. The cold spot is just one of many features that have followed this rhythm. Some of the features have eventually been resolved. Others remain open. The cold spot is, at present, among the open ones. We will, in time, learn more. The polarization measurements of the next decade should help. The galaxy surveys of the next decade should help. The theoretical work continues. Let me hold one more aspect of how cosmologists think about anomalies like the cold spot. There is a phenomenon sometimes called the look elsewhere effect, which is relevant to evaluating significance. The look elsewhere effect says, if you search a dataset for any kind of unusual feature, you are likely to find some, even if the data follows the predicted distribution exactly. The reason is that in any sufficiently detailed dataset, there will be regions that by chance happen to look unusual. For the cold spot, the question is whether we found it because we were looking for cold spots specifically, or because we happened to notice it among the many possible features in the data. The two situations have different implications for the significance. If we were specifically looking for a cold spot of a particular size and shape, then finding one with a 5-degree diameter and 70 microkelvin depression would be a meaningful detection. The significance estimates would be straightforward, but if we were looking for any kind of unusual feature, and we happen to find a cold spot, then the significance is reduced. We have many opportunities to find unusual features, and one of them being a cold spot is less surprising than it might initially seem. The actual situation for the cold spot is somewhere between these two cases. The cold spot was identified through wavelet analysis, which is sensitive to a particular range of feature scales. Within that range, the cold spot is the most unusual feature. The look elsewhere effect must be accounted for, but the analysis has done so. The resulting significance, with appropriate corrections, is in the 3 to 4 sigma range. This is the estimate I have been quoting. Whether the significance is sufficient to demand explanation beyond the standard model is, in some sense, a matter of judgment. Some cosmologists consider it sufficient. Others consider it borderline. The matter continues to be debated. What is clear is that the cold spot is real and is interesting. Beyond that, the interpretation is open. If you have come here to rest, let this carry you. The cold spot is not threatening. It is a small anomaly in a vast measurement. It sits quietly in the southern sky in the constellation Eridanus at a particular celestial coordinate. It is one of the many features of the cosmos that we have in our small recent moment learned to measure. Whether it is, in fact, evidence of another universe touching ours, or simply a chance fluctuation, or the imprint of a supervoid, we will continue to investigate. The work is ours. The cosmos is the universe's. Stay with me here for one more moment. Let me also walk through what would happen if the bubble collision hypothesis were definitively confirmed. The discovery would, as I have said, be one of the most significant in the history of physics, but the practical consequences would be limited. We would know that another universe exists. We would know in some sense that our universe is not alone. We would know that in the deep past our universe interacted with another. We would know the direction of the other universe. What we would not be able to do is communicate with the other universe. The collision happened in the inflationary past. Both universes have continued to expand since. The other universe, by now, is causally disconnected from us. There is no possible way for a signal to travel between us. We would also not be able to visit. The other universe is, in the cosmological geometry, outside our observable region. The cosmic expansion has placed it far beyond anywhere we could ever reach. The cosmic horizon limits our access. The other universe is, in this sense, fundamentally unreachable. What we would have is the imprint, the cold spot, as a record of the past collision. The imprint would be the only evidence of the other universe that we could ever access. So the discovery, if it occurred, would be intellectually profound but practically isolated. We would know more about the deep structure of reality, but we would not gain any new capabilities in everyday life. This is, in some sense, characteristic of much of fundamental physics. The discoveries deepen our understanding without necessarily affecting our daily existence. The neutrino exists, the Higgs boson exists, dark matter exists, but these facts do not change how we go about our lives. The cold spot, if it is a bubble collision imprint, would join this list. A profound discovery with limited practical impact, expanding our cosmological self-understanding without changing our day-to-day reality. This is the kind of discovery that modern cosmology can produce. The CMB, as I have walked through, is our most direct record of the early universe. It records the state of the cosmos at a particular early moment. By studying it, we learn about that moment. The features in the CMB, including the cold spot, are part of the record. Each feature has its history. Each feature has its potential explanations. Each feature is part of the cumulative picture we are building of cosmic history. The cold spot is one such feature. Its history may, in some sense, predate even the recombination. It may, in some interpretations, encode information about events from inflation or before. If so, the cold spot is one of the deepest observational records we have. Whether it is in fact such a deep record, we do not yet know. The investigation continues. What we have at present is the cold spot. We have its mystery. We have our candidates for explanation. We have our methods of analysis. We continue. Now let me bring this closer one final time. The cold spot, regardless of its ultimate explanation, has taught us something. It has taught us that the standard cosmological model, while excellent, is not perfect. Small features remain unexplained. The standard model may need refinement. Let me also walk through the historical pattern of how cosmological mysteries are eventually resolved. The history of cosmology contains many features that were, in their time, unexplained or anomalous. Some were eventually resolved, some are still being worked on. The pattern of resolution is, in some sense, the natural rhythm of the field. The microwave background itself, when it was first detected, was an anomaly. It did not fit the steady-state cosmological model that was popular at the time. The Big Bang theory, which predicted the CMB, was thereby supported, but the standard model was, in some sense, modified to include a hot early phase. Dark matter, when its existence was first inferred from galactic rotation curves and other gravitational measurements, was an anomaly. The visible mass of galaxies did not account for the observed dynamics. The standard model was modified to include a non-luminous matter component. Dark energy, when its existence was inferred from supernovae observations, was an anomaly. The expansion of the universe was found to be accelerating, contrary to expectations. The standard model was modified to include a cosmological constant or some equivalent. In each case, the anomaly was real and significant. In each case, the standard model was extended to accommodate it. The extensions were not, in themselves, dramatic. They were modest additions that allowed the model to fit the data. The cold spot may follow this pattern. It may eventually be explained by some modest extension of the standard model, perhaps a recognition that we live in or near a supervoid. Perhaps a recognition that some specific primordial fluctuations are larger than the average expectation. Perhaps something else. Or it may, like the existence of dark matter and dark energy, be a marker of something more substantial, a pointer to new physics, a clue to the existence of something we have not yet integrated into our picture. We do not yet know which kind of anomaly the cold spot is. The cold spot has also, in some sense, expanded our cosmological imagination. The possibility that we might have indirect evidence for another universe is, in itself, a striking idea. Whether the cold spot provides such evidence or not, the discussion of the possibility has expanded what we consider cosmologically plausible. This is, in some sense, what unusual features can do. They prompt us to consider possibilities we had not previously considered. They expand the space of hypotheses we take seriously. The cold spot has expanded our hypotheses. The hypotheses include the multiverse, the bubble collision, the deep encoding of pre-recombination events. Each of these, if true, would change our cosmological picture significantly. We do not know if any of them is true, but we have, by careful study of the cold spot, come to consider them seriously. This is one of the textures of how cosmology develops. Features in the data prompt new hypotheses. The hypotheses are studied. The picture, slowly, refines. Let me hold one more aspect of the multiverse picture. If eternal inflation is correct, then the multiverse contains, in some sense, an infinite number of bubble universes. Each bubble has its own physics. Each has its own cosmic history. Each has, presumably, its own observers, if observers can form in it. The total structure is, in some sense, unimaginably vast. The multiverse contains every possible configuration of physics consistent with the inflationary dynamics. Some bubbles may have life, some may be sterile. Some may have very different physical constants from ours. We, in our particular bubble, are a small portion of this vast structure. Most of the multiverse is causally disconnected from us. We can never directly observe most of it. We can only perhaps see imprints of past interactions. Like the cold spot might be, this is in some sense a humbling picture. We are a small bubble in a vast metaverse. Our particular cosmic history is one of many. The cosmic events we observe are local to our region. The multiverse, if real, transcends our normal cosmological self-understanding in a profound way. Most of physics has, in recent decades, expanded the scale of what we consider. From planet to solar system, to galaxy, to local group, to supercluster, to observable universe. Each scale was, at its time, a major expansion. The multiverse, if real, would be the next major expansion. Beyond our observable universe lies the rest of the metaverse, with its many bubbles. We are a small part of this larger structure. We do not know if the multiverse is real. We have no direct evidence. We have, at most, indirect hints like the cold spot, which may or may not be a bubble collision imprint. But the possibility is, in some sense, alive in the literature. We continue to investigate it. We continue to consider what it might mean. Let me also walk through one more aspect. If the cold spot is, in fact, a bubble collision imprint, we might wonder about the timing. The collision in this picture occurred during inflation. The inflation lasted a tiny fraction of a second in the very early universe. The collision would have occurred at some particular moment during that brief inflationary period. The energy of the collision would have been, by current models, enormous. The inflationary energy scale is, by some estimates, on the order of 10 to the 16th giga-electron volts. That is roughly 10,000 trillion times the energy of any particle we have ever produced in laboratory experiments. The collision at such energies would have involved physics we cannot at present study directly. The physics of inflation is, in many ways, beyond our experimental reach. We can only model it theoretically and constrain it through indirect observations. If we had direct evidence of a bubble collision in the form of a confirmed CMB imprint, we would have, in some sense, a unique window into the physics of the inflationary epoch. We would have a record of an event that occurred at energies far beyond what we can produce. The record would tell us, indirectly, about the physics at those energies. This is, in some sense, the unique scientific value that the bubble collision hypothesis offers. Confirmation of the hypothesis would not just tell us about the multiverse, it would tell us about the physics of inflation. But, again, we do not have confirmation. We have only the possibility. The cold spot may or may not be such an imprint. We continue to study it. We continue to investigate. Now let me come, slowly, to a quiet close. The cold spot is in the southern sky tonight. It is in the constellation Eridanus. It is approximately 5 degrees across. It is approximately 70 microkelvins colder than the surrounding cosmic microwave background. We do not know why. We have candidate explanations. We have methods of investigation. We have future experiments planned. The investigation continues. Let me also walk through what kind of confirmation, in principle, could establish the bubble collision hypothesis. Confirmation would require, at minimum, the following. First, the cold spot would need to have polarization properties consistent with a bubble collision, and not consistent with the chance fluctuation or supervoid explanations. The polarization signature is, in principle, distinguishing. Second, the cold spot would need to be one of multiple similar features, ideally multiple. A single feature might be a chance fluctuation. A pattern of features, all matching the bubble collision template, would be much more compelling. Third, the theoretical framework of eternal inflation would need to be confirmed by other means, possibly through constraints on the inflationary models from particle physics or other observations. None of these conditions is, at present, met. The polarization data is not yet precise enough to distinguish explanations for the cold spot. We have not found multiple confirmed bubble collision imprints. Eternal inflation remains theoretically interesting, but not directly confirmed. So the path to confirming the bubble collision hypothesis is long. It involves multiple lines of evidence that, individually, are difficult to acquire. If, over the next several decades, all these lines of evidence accumulate, we could, in principle, become confident that the cold spot is a bubble collision imprint and that the multiverse exists. The accumulation would take time, but it is, in principle, possible. If, on the other hand, the lines of evidence do not accumulate, the hypothesis will remain speculative. The cold spot may eventually be explained by some other mechanism, or it may remain unexplained. This is the long arc of the investigation. We do not know how it will end. We continue to do the work. If you have come here to rest, let the small anomaly in the southern sky settle into your thinking. It is small. It is mysterious. It is not threatening. It is in some sense one of the open puzzles of modern cosmology. It sits there in our data, awaiting its explanation. Whether the explanation will eventually be ordinary or extraordinary, we do not know. The investigation will, in time, tell us. Let me hold for a moment what the title of this video means. Another reality is leaking into ours. The phrase is, in some sense, the most extreme interpretation of the cold spot. If the bubble collision hypothesis is correct, then another universe has, in the deep past, left its imprint on ours. The imprint is, in a metaphorical sense, a leakage from that other universe into ours. The leakage is, of course, not active. The other universe is by now causally disconnected. The imprint is a frozen record of past interaction. Nothing is currently leaking in any active sense. But the word captures something true about the picture. Our universe is not, in this interpretation, isolated. It has been touched. The touch left a mark. The mark is what we see in the CMB. The spreading in the title refers, in some sense, to the propagation of the imprint over cosmic history. The imprint has been part of the cosmic web from the very early universe. It has been spread, by cosmic expansion, across the surface we now call the recombination surface. It has been preserved in the CMB, so the imprint is not, in fact, spreading in any active sense. It has been there for nearly the entire age of the universe, but the language captures the picture of an influence reaching us from another universe. This is the metaphor. The science behind the metaphor is, as I have walked through, speculative. The cold spot may or may not be a bubble collision imprint. The other universe may or may not exist. But the language is, in some sense, evocative. It captures what would be true if the most exotic interpretation is correct. For tonight's purposes, we have walked through what the picture would mean. We have walked through the science behind it. We have walked through the alternative explanations. The cold spot remains, in some sense, the most mysterious feature in our cosmic microwave background data. It awaits its explanation. We continue to investigate. For now, we have the cold spot. We have walked through what it is and what it might mean. That is what we have done tonight. Let me also walk briefly through how the cold spot relates to the philosophy of fundamental physics. The cold spot, like many features in modern physics, sits at the boundary of what we know and what we can know. We can measure it with precision. We can study its properties. We can compare it to the predictions of various models. We can debate its interpretation. What we cannot at present do is determine its true origin. The various candidate explanations are, by current data, indistinguishable. Future data, particularly polarization measurements, may eventually distinguish them. But for now, the matter is open. This is, in some sense, the texture of modern fundamental physics. Many features and phenomena are studied. Many explanations are proposed. Few are definitively confirmed. The work proceeds by accumulation of constraints and refinement of models, rather than by dramatic single discoveries. The cold spot is one of the features in this slow accumulation. It is one of the puzzles that the field is working on. The work continues. We, as observers tonight, have walked through what the work has produced so far. We have considered the puzzle. We have considered the candidates for explanation. We have considered the implications of the various candidates. We have not solved the puzzle. We have perhaps come to understand it more clearly. Let me also walk briefly through the question of how we should think about strange features in our data, like the cold spot. The cosmological data we have is rich and complex. It contains many features. Most of them are well explained by standard models. A few are anomalous. For each anomalous feature, the natural questions are, is it real? Is it significant? What could explain it? Each question requires careful analysis. The cold spot has been worked through each of these questions. It is real, by careful statistical analysis. It is significant, in the sense that its probability of occurring by chance is small. It has multiple candidate explanations, none of which is currently confirmed. This kind of careful working through is, in some sense, what science does with anomalous features. The features are not dismissed. They are not exaggerated. They are studied carefully, with appropriate methods. The result of this careful study is, sometimes, that the features turn out to be uninteresting, simply chance fluctuations or instrumental artifacts. Sometimes the features turn out to be markers of new physics. Most often they turn out to be in the middle, suggesting some refinement of our understanding but not requiring dramatic revision. The cold spot is, at present, in this middle territory. It is real and significant, but not necessarily a marker of new physics. The investigation will, in time, place it more precisely in the spectrum of possibilities. This is the work. We are watching it unfold. Let me also hold one final thought. The very fact that we can detect a 70 microkelvin temperature depression in a sky-wide measurement of cosmic radiation is, in itself, a remarkable accomplishment. The cosmic microwave background fluctuations are tiny, only 1 part in 100,000. Detecting the cold spot's depression requires extreme precision. We have achieved this precision. The Planck satellite, in particular, mapped the CMB at unprecedented levels of detail. The data we now have allows us to study features that, only decades ago, would have been below our detection threshold. This is one of the small wonders of modern astrophysics. We have, in our brief time as observers of the cosmos, developed instruments that can detect minuscule features in radiation that has been travelling for 13 billion years. The cold spot, in this sense, is a triumph of measurement. Its existence is established. Its meaning, while still debated, is being actively investigated. We are doing this work. We are, in some sense, paying attention to features of the cosmos that no one paid attention to before. We are extracting information that, until recently, was inaccessible. This is what modern observational cosmology can do. The cold spot is one of the many fruits of this capability. Whether it represents evidence of another universe, or a chance fluctuation, or a supervoid imprint, the very fact that we can study it is, in itself, a noteworthy achievement. Let me hold also the cooperative nature of this work. The cold spot has been investigated by many groups, across many institutions, using many different techniques. Each contribution adds to the cumulative picture. The full understanding, when it comes, will be the product of many hands. This is one of the textures of modern cosmology. The questions are too big for any individual or small group. They require sustained effort across the field, with different groups working on different aspects. Different groups have specialized in different aspects of the cold spot investigation. Some focus on the statistical analysis of CMB data. Some focus on the galaxy surveys that probe the supervoid hypothesis. Some focus on the theoretical work on eternal inflation and bubble collisions. Some focus on the polarization measurements that may eventually distinguish explanations. The cumulative work over the past 2 decades has been substantial. Hundreds of papers, many independent analyses, many proposed interpretations. The cold spot has become, in some sense, one of the well-studied features of modern cosmology. Let me also hold what the cold spot looks like in the context of the cosmic neighborhood. The cold spot's celestial location is in the constellation Eridanus in the southern hemisphere. Eridanus the river is a long, winding constellation that spans many degrees of sky. The location of the cold spot, when mapped onto the cosmic background, falls in a particular small region of Eridanus. Specifically, the center is at right ascension 3 hours and declination minus 19 degrees approximately. When we look in that direction with optical telescopes, we see the usual array of stars in our own galaxy. The stars are foreground objects. They are not, in any direct way, related to the cold spot. Beyond the foreground stars, deeper in the same direction, we see distant galaxies. Various surveys have catalogued the galaxies in that region. The galaxy distribution in the direction of the cold spot is, by current best data, somewhat below average, though the size of the underdensity is the subject of debate. If the supervoid hypothesis is correct, the underdensity extends to a distance of approximately 6 billion light-years from us, in the direction of the cold spot. Beyond the supervoid, deeper still, is the cosmic microwave background itself. The CMB is emitted from a sphere at the surface of last scattering, approximately 45 billion light-years away, in co-moving distance. The cold spot is a feature on this sphere, in the direction of Eridanus. So when we look at the cold spot, we are looking through, in some sense, multiple layers of cosmic structure. Foreground stars, distant galaxies, possible supervoid, CMB surface of last scattering. Each layer is at a different distance. Each contributes, in its way, to what we see. The cold spot itself is a feature of the deepest layer, the CMB. The other layers, the supervoid in particular, may affect how the CMB looks to us via the integrated Sachs-Wolfe effect. But the cold spot is, in its essence, a feature of the cosmic background, not of the foreground. What has not yet emerged is a consensus on its explanation. The various candidates remain in competition. The data has not yet been definitive. This is not unusual. Deep questions in fundamental physics often take decades to resolve. The cosmic background radiation itself took decades from prediction to discovery. Dark matter has been studied for over half a century without identification of its constituent particle. The interpretations of quantum mechanics have been debated for nearly a century without resolution. The cold spot may follow a similar pattern. Resolution may take decades, or it may come quickly with the next generation of CMB experiments. We do not know. What we know is that the investigation continues. The field is engaged. The data is improving. The picture is, slowly, refining. Hold this. The work of observation, the work of measurement, the work of theoretical interpretation. These are the components of the larger enterprise. We participate in this enterprise. Tonight we have walked through one of its products. Let me hold one final image. The cold spot exists in our cosmic data. Our cosmic data is, in some sense, a record of the universe. The record has been built up by careful observation across many decades. The cold spot is one of the entries in the record. The entry is unusual. The entry is interesting. The entry has not been fully explained. This is where it sits, in the record, awaiting its full explanation. subject to ongoing investigation. We have walked through it tonight. We have considered its history. We have considered its candidate explanations. We have considered its implications, including the most exotic possibility that it represents an imprint of contact with another universe. The exotic possibility is, by current best understanding, unlikely. But it is not ruled out. This is what we have at the close of tonight. A particular feature in our data, a particular range of possible explanations, a continuing investigation. The work goes on. Let me hold one more aspect. The cold spot is, in some sense, an invitation to think about the boundaries of what science can investigate. Most of the cold spot's candidate explanations are within our normal scientific reach. Chance fluctuation, supervoid, primordial physics, these are all things we can study with our standard methods. The bubble collision hypothesis pushes the boundaries. It invokes phenomena from outside our universe. It invokes events from before our universe's particular cosmic history. It invokes the multiverse. This is, in some sense, the edge of what science can address. We can hypothesize about other universes. We can derive what their interactions with us might look like. We can search for the predicted signatures, but we cannot directly observe other universes. They are, by the cosmological geometry, beyond our horizon. We can only see their imprints, if any exist. The imprints, even if found, would be indirect evidence. This is one of the textures of working at the cosmological frontier. The questions push against the boundaries of what is observable. Some questions can be addressed. Others may be permanently out of reach. The cold spot, as a possible bubble collision imprint, is on the boundary. We can investigate it. We may eventually determine its origin. But the determination, if it favours the bubble collision interpretation, would be unique evidence of phenomena that we can never directly observe. This is in some sense a remarkable position. Science can, in some cases, give us indirect access to phenomena that are otherwise inaccessible. The cold spot may be one such case. We continue to investigate. The cold spot, real, statistically unusual, unexplained, one of the open puzzles. We continue. Thank you for staying with me through this story.